Hello, this little video is about another method of figuring out when a polynomial is irreducible over the rationals, and bears the name of Eisenstein criterion. It's a specific works under specific conditions, very special result, but it is very easy to check and so is very powerful. So let's start with a polynomial with integer coefficients. Call them fi's, and they run from 0 to some stopping point called the degree, if it is non-zero. Let's fix a prime. Let's assume that coefficients are such with respect to this prime that the leading coefficient, this number t coefficient, is not divisible by the prime. All other coefficients are divisible, so I is less than p. And moreover, the very first, the 0th coefficient, is not divisible rather by the square of the prime. Is divisible only by the first power. Then, under these conditions, we can be sure that f is irreducible over the rationals, or even over the integers. Let's argue for that by assuming the opposite. Assume that we have a factorization into a product of two rational polynomials but by Gauss's lemma, these polynomials can be chosen to have integer coefficients. And after that, let's take this equation and reduce mod p. So let's look what happens with the reductions of these polynomials, which are polynomials with coefficients in the field of p elements. We have the reduction of f being equal to the reduction of a times the reduction of b. And the conditions are designed in such a way that the reduction of f is specifically simple. So we say that the leading coefficient is not 0 mod p, let's call it c. And then we have the coefficient for the dth power, for this highest power. Everything else will be vanishing mod p, it will be divisible mod p. So that is the reduction of f. And there are not that many ways it can factorize into a product. By unique factorization in this polynomial ring with coefficients in the field, the factors can only be powers of t, monomials, powers of t, which complement each other to the dth power. So if I say this power is r, then the power in b monomial will be d minus r, and then there will be some coefficients like u and v, which will give me my polynomial f. So that is the reduction of a, and that is the reduction of b. They have to be. We can just say that the coefficients multiply into c. That is not so important. What is important is the conditions on the three terms of a and b we get from these shapes of the reductions. We can be sure that the 0th coefficient of a, we can write it as the value of a at 0, is divisible by p. And so is the 0th coefficient of b. Well, because after reducing we don't have them. But then we could look at what happens with the 0th coefficient of our original polynomial f. Because of this factorization, it will be the product of the two. One for b, the 0th coefficient, and then the other for a. And each of them is divisible by p, so the whole thing will be divisible by p squared. But we explicitly forbid it. This is nothing but the 0th coefficient in this expansion. And we forbid by the condition p squared to divide it. So that is a contradiction. We are done. We assume that we have a factorization. We run into an inevitable contradiction. Factorization should not exist. Our polynomial is irreducible. Let's look at applications of this result. I'll just have one simple application. Let's assume that my polynomial is t to the n is arbitrary, minus, say, 6. Then I can choose my prime to be either 2 or 3. In any of those choices, I have the conditions of the Eisenstein criterion. All but the leading coefficient are divisible by 2. Well, the absent, hence divisible, and the one which is not, the free term, is divisible by 2. And then the free term is not divisible by 2 squared, by 4. Hence, this polynomial is irreducible. Well, that's it for now. Thank you. Goodbye.